One of the most common applications of this subject is to infer something about the population based on sample data. So let's say I want to calculate student income. So I'll take a sample, let's say my Mondays class, and calculate some sort of average income to infer something about the population student income. The only problem there is that different samples will give me different averages. So to take that into consideration, that variability, we'll be talking about confidence intervals. Okay, so again, let's utilize the same examples as I've been using before. Let's say we have a bank manager who wants to estimate students' income. So let's say he knows, or let's say we know that the population average of students' income is $11,000. Okay, so let's say he takes a sample of my Monday class, and based on that sample, he calculated a sample average income of $9,000. Or let's say he goes and takes a sample of my Tuesday class, and he finds a sample average of $13,000. Or let's say my Thursday class, and he finds a sample average income of $8,000. Or on my Friday class, let's say a sample average of $12,000. So we can see here different samples will give us different estimates of the population average. So usually we would take one sample and we would infer something about the population. But we can see that here different samples does give about different population estimates. And so to take this variability into account, it might be more appropriate to construct what's known as confidence intervals. So for example, let's say I can make the following statement. I am 90% confident that the population mean lies between, let's say, $9,000 and $13,000. Okay, so how do we visualize this confidence intervals? At least the mechanics of it. We can look at the following bell curve. So let's say we know the population mu is in the middle. Essentially, we want to be able to find x1 and x2, values of x1 and x2. We can say between x1 and x2, for example, I'm 90% confident that the population parameter lies. Okay, so how would we usually denote that in mathematical notation? Well, usually if I want to say 90%, I can write it as 1 minus alpha is equal to 90%. So 1 minus alpha, or 90%, represents that area between x1 and x2. So you might be asking, then what does alpha actually represent? Well, it's given that the middle bit represents 90%, our alpha must therefore represent these other areas, these tails. So since we have two of these tails, one of these tails will be alpha divided by 2, representing about 5%, and the other tail would be also similarly alpha divided by 2, representing 5%. So if we could sum all these areas up, guess what value it will come up to? Well, 5% plus 90% plus 5% will give us 100%. And again, it's just utilizing that fact that all areas under the curve must add up to 1. Or if you sum up all probabilities, they must equal to 100%. Okay, as noted in that sentence there. Okay, so when calculating confidence intervals, the first step is to decide which confidence interval formula should you be utilizing. And there's 3 main formulas here. First one, if your population standard deviation is given, so it's known, then you should use this formula. If your population standard deviation is unknown, so in this case, the question might give you, let's say, instead of giving you a population standard deviation, it might be giving you, and I'll just highlight it, it might be giving you some sort of sample standard deviation, then you should use this formula, which utilizes the t-distribution. And if you've got a question regarding or in relation to proportions, then this is the formula of interest. So those are the 3 main formulas if you're going to be calculating confidence intervals. Whilst in this topic, we are introducing a new concept, confidence intervals. It's really just an extension of our previous topic. So if you have a look at it, we're still utilizing areas under the bell curve, but just at a different angle. And that's it. I'll see you guys next time.